So in this video, we're going to be looking at graphs of several more types of functions under the lens of continuity. So the first function we're going to be looking at is f of x equals ln of x plus 3. I've graphed it here. You can see it has a vertical asymptote at x equals -3. But more importantly, the graph of f of x equals ln of x plus 3 is the graph of g of x equals ln of x, just shifted 3 units to the left. So the vertical asymptote in ln of x is x equals 0. In ln of x plus 3, it's x equals -3. ln of x is going to be passing through the point 1, 0, while ln of x plus 3 passes through -2, 0. ln of x is going to pass through the point e, 1. E is about 2.718, so e is approximately 2.718. So you'd expect ln of x plus 3 to pass through e minus 3, 1. E minus 3 is going to be about 2.718 minus 3. That looks like it'll be -0.282. I believe that's correct. Not sure. Yeah, it looks like it'll be passing through -0.282, 1. And that seems about right from the graph. So everything in ln of x plus 3 will just happen 3 units sooner. So you can apply you can put in a number for a value of x like 3 smaller than ln of x, and because you're adding 3 to it, the ln function will be applied 3 units sooner than in the case of ln of x. And so if you just look at this function, ln of g of x equals ln of x, you can see it as a vertical asymptote at x equals 0. So it's really undefined for values of x less than or equal to 0. It looks like it's continuous wherever it's defined. So it's continuous for all values greater than 0. Similarly, ln of x plus 3 is continuous for all values of x greater than -3. And both of these functions just continue in this fashion in an increasing manner, way out as x tends towards positive infinity. Really, this is the case for all logarithmic functions of the form log base a of x, or I should say h of x equals log base a of x, where a is greater than 1. They're all continuous within their domain, and even if you had log base a of x plus c, it'll also be continuous in its domain. Pretty much any logarithmic function is continuous within its domain of definition. So it's right here. All logarithmic functions are continuous within their domains of definition. And that's really the same thing as saying they're continuous for all points within their domain of definition. Now we're going to look at sine of x and cosine of x. So in blue I've drawn f of x equals sine x, and in green we have g of x is cosine of x. And both of these functions are continuous for any real value of x. I've shown the interval, both functions in the interval -2 pi to 2 pi, so that's a closed interval here. I've drawn arrows showing that they continue, but they essentially, like cosine of x, is just going to repeat in this fashion. This is one period of cosine of x. This is another period of cosine of x, pretty much every other period as you go on. As x tends to positive and negative infinity is going to look identical to to this period and this period. So this cosine of x is continuous for all real values of x. Similarly, sine of x, you can see it's doing the same thing between 0 and 2 pi as it is between negative 2 pi and 0. So you can expect that it's going to really continue doing the same thing as x tends to positive and negative infinity. So both sine and cosine are continuous for all x, all real x, I should say. But let's say instead of cosine of x, we had h of x equals 10 cosine of 2x minus pi over 2 plus 5. Is this function also continuous for all x? Well, let's see. Well, how is this function different from cosine of x? Well, for starters, it's going to be shifted pi over 2 units to the right and 5 units up. And this 2 in front of the x is basically it's going to make the function period be pi instead of 2 pi. So this function will happen twice as fast as the cosine function shown in green here. And this 10 in front is going to change the upper and lower bounds of the function. Instead of being well, I guess it's shifted 5 units up. So instead of this shift would make it, instead of being negative 1 to 1, or it should be the closed interval, negative 1 to 1, h of x, it'll be, so I should say instead of, so this is shifting, this is the result of shifting up 5 units. Instead of that, we'll have, well, oops, I wrote, should be negative 1, not 1 minus, so negative 1. Add 5 to negative 1, you'll get 4. Add 5 to 1, you'll get 6. So it'll range from 4 to 6. But you also, in addition to that, you kind of multiply everything by 10. So instead of ranging from 4 to 6, so this is I'll just say coefficient of 10. Coefficient of 10 instead of, so this is our new base ranging from 4 to 6, h of x ranging from 4 to 6, we'll have h of x ranging from 40 to 60. These two changes here don't affect the value of the range of h of x. They this 2 again just makes the function go twice as fast. The period's pi instead of 2 pi, and this pi over 2 or minus pi over 2 shifts the function pi over 2 units to the right. But what does that do? What do all these changes do to the continuity of the function? Well, the answer is really nothing, right? If you move a function, shift a function to a new location, does that change the continuity? Let's say the original function is continuous for all real values of x. Well, the new function is also going to be continuous for all real values of x. If you make that function, that cyclic function, which is going to go through, or periodic function, if you go through each period twice as fast as you would have otherwise, does that change the continuity of the function? Well, no, it doesn't. And then does stretching it out by a factor of 10, is that going to change the continuity of the function? That's not going to do anything either. So really all functions all variants of sine and cosine, I'll say, put an asterisk here, all variants of sine x and cosine of x of the form, I don't know, we'll say f of x equals a sine of bx plus c plus d. And each of these can be positive or negative numbers, rational, irrational, as long as they're real numbers. And again, this a just corresponds to this 10 here. This b corresponds to this 2 here, so how fast the function repeats. And c corresponds to this minus pi over 2 here, so the horizontal shift. And d corresponds to the 5 here, so the vertical shift. So all variants of sine x and cosine of x of this form are going to be continuous for all real values of x. Now we're going to look at the function f of x equals tangent of x, and hopefully you remember that tangent of x is defined as sine of x over cosine of x. And you can see here we have vertical asymptotes at every odd multiple of pi over 2. So even multiples of pi over 2 like 0 and pi, we're okay, but here we have infinite discontinuities at odd multiples of pi over 2. So this is the asymptote x equals pi over 2. This is the asymptote x equals 3 pi over 2. X equals negative pi over 2. X equals negative 3 pi over 2. And so forth. So this is one period of the tangent function between negative pi over 2 and pi over 2. And it just kind of repeats in this fashion. But you do have infinite discontinuities at every odd multiple of pi over 2. To convince yourself of that, you hopefully remember the unit circle definition of sine and cosine. Sine is the y-coordinate, cosine is the x-coordinate. And we're going to be starting at 0 degrees, or 0 radians. This is also 2 pi radians once you make a full circle, or 4 pi, etc. Pi over 2 can be thought of as 5 pi over 2, just adding 2 pi to pi over 2. And okay, so let's look at 5, or let's look at, as we approach pi over 2, coming from values less than pi over 2, sine is positive and very, very close to 1. Cosine is positive and very, very close to 0. So when you have like something like 0.999999, remember tangent sine divided by cosine, divided by 0.0001. As this gets closer to 1, as this gets closer to 0, this is gonna get closer to positive infinity, right? Now when we're looking on the other side of x equals pi over 2, sine is going to be positive and very close to 1. Cosine is going to be negative and very close to 0. So we're going to have a situation like 0.99999 divided by negative 0.00001. And as the closer you're talking to this pi over 2, the closer sine is going to be to 1, and the closer cosine is going to be to 0, but it's still going to be a negative number. So this is going to be negative infinity on this side of, immediately on this side of pi over 2. It's going to be really, really large negative numbers. And the same is kind of the case for on either side of every other odd multiple of pi over 2. So if you notice here, when the denominator is 0, or when x is an odd multiple of pi over 2, that makes cosine of x 0. With the denominator 0, we have infinite discontinuities. But you might be wondering, oh, is that so? When the denominator is 0, is that generally the case? Is that always the case that you will have an infinite discontinuity? And the answer is no. And I'm going to illustrate that via another example. So here we have the function g of x equals x squared minus x minus 6 in the numerator. In the denominator we have x minus 3. So x squared minus x minus 6 over x minus 3. And hopefully you can see that the numerator factors to x minus 3 times x plus 2. We have x minus 3 in the denominator. If we divide both numerator and denominator by x minus 3, we get x plus 2. But in order for us to have done this step, x cannot be equal to 3, right? If it is equal to 3, that would necessitate dividing the denominator by 0. We cannot do that. Well, dividing both numerator and denominator by 0, and we cannot do that. So what's this graph going to look like? Well, it's going to look like it's going to basically be a line, y equals x plus 2, right? So line is slope 1 with intercept y-intercept 2. But it's going to have a hole. Where's it going to have a hole? It's going to have a hole at x equals 3. And the y value there will be, well, 3 plus 2, 5. It's going to have a hole here at 3. Well, is that right? So I've drawn the hole at 3, 4. It should be at 3, 5 here. Right, yeah. So it'll have a hole here. And in this case, you have a removable discontinuity. So why is this a removable discontinuity? Well, you can redefine g of x. There exists another function, we'll call it capital G of x. It's going to be identical to lowercase g of x except at this point of discontinuity. So this capital G of x is going to equal x squared minus x minus 6 over x minus 3 when x is not equal to 3. And at 3 it's just going to equal 5. Now this function basically fills in this hole here, so we have a removable discontinuity. And again, this is another situation in which our pointed discontinuities where the denominator would be 0. And in the prior case we looked at, tangent of x, we had infinite discontinuities when the denominator was 0 at odd multiples of pi over 2. Because denominator of tangent of x is cosine of x, and at odd multiples of pi over 2, cosine is 0. But in this case, when 3 is 0, we have a removable discontinuity. So if you're looking at a function where the denominator is 0 and you're asked to identify the type of discontinuity present in the function, the answer is going to really vary on a case-by-case basis. And hopefully with some practice you'll be able to figure out which situation you're dealing with.